Welcome again. This is, we have one more session next month for this academic year. Thank you again for joining and supporting this series. Today we have the pleasure to have Robert Rodini talk on Fibonacci numbers. A few words about Robert. I met him recently, since myself I'm new here. He received his education, mathematics BA in the University of Pennsylvania. Later on, he received his MS Computer Science at Villanova University and MA in Mathematics as well, Villanova University. Obviously, Robert has done very many things in his life. Software engineer at major systems manufacturer. He had his own startup company, financial services company, and he has dedicated last 6 years as an instructor at Delaware County Community College as well as Penn State University. Now, you sent us the synopsis, and I went through the synopsis, and I'm not a mathematician, so my background is very limited here. I'm a biologist, and I was wondering what rapid progeneration has to do with these numbers. I was simply curious to see what.
I have several slides on rabbits. So
well, let's see. We might learn something here.
Okay.
Without further ado, I present you over. Please don't forget to sign in.
Can you hear me okay? I think. Yes, okay, good. Because I need this, so I don't project too well. I'm Mr. Rodini. I'm an adjunct here, as mentioned. I mostly teach computer science courses, Java and JavaScript, although in the past I have taught several math courses. And you can say that there's a STEM gene in my family because my older brother has a PhD in mechanical engineering. My younger brother has a PhD in chemistry. Sorry, Mom, I just have master's degrees, no PhD. Today I'm going to talk about the Fibonacci numbers, or the Fibonacci sequence, which are very fascinating. But first I want to ask, did everyone bring a pencil and a piece of paper? Because I'm going to have you do a calculation, all right? But most of all, did you bring your algebra? Because this lecture, uses a lot of algebra. Algebra 2, nothing beyond algebra 2. Okay, so I hope you can follow along. And just raise your hand if you think I'm going a little too fast. So let's start talking about the Fibonacci numbers, or the Fibonacci sequence. Here they are along the bottom: 1, 1, 2, 3, 5, 8, 13, 21. Now the Fibonacci numbers have a strong geometric interpretation, as shown in this rectangle with the spire within it. So I'm going to start at the center of the spire. There are two 1 by 1 squares adjacent to another, and inscribed in each of those squares is a quarter circle. And then above the two 1 by 1s is a 2 by 2 square, also with an inscribed quarter circle. To the left of that is a 3 by 3 square, below 5 by 5, to the right 8 by 8, 13 by 13, 21 by 21. So you see that we're duplicating this, the side length of the square is duplicating the Fibonacci numbers. So who was Fibonacci? Well, he was both a merchant and a scholar. As a merchant, he traveled around the Mediterranean world to do business, but he was also a scholar. So at every port that he stopped, he sought out the local mathematical scholar and basically picked that person's brain to see what mathematics he could learn from that person. And one of the major things he learned was the Hindu Arabic numerals, which were in use in the Arab world. Are familiar numbers like 0, 1, 2, 3. And he realized that this was the way to do arithmetic. Before, they were using Roman numerals, right? Did you ever try to add, subtract Roman numerals? It's like, can't do it. So he realized that they had a better system, and he brought it back to Italy and started promulgating it. He also learned new topics in mathematics from these Muslim scholars. And this came about because for the previous several centuries, the Muslim world had adopted Greek mathematics and extended it into the area of algebra. So he learned some algebra during his journeys also. At one point, he returned to Italy and he wrote all the math that he knew down in a famous book called Liber Abaci, or the Book of Calculation. This book was widely duplicated and had a powerful influence on the development of Western mathematics. Fibonacci also is known as Leonardo of Pisa, which I think is a pretty cool name too. In his book Liber Abaci, he described the famous rabbit problem. So here is an image of one of the pages of the Liber Abaci, and it describes the problem, which I'll read to you in its original form. A certain man had one pair of rabbits together in a certain enclosed place, and one wishes to know how many are created from the pair in 1 year, when it is the nature of them in a single month to bear another pair, and in the second month those born to bear also. Because the above written pair in the first month bore, you will double it. There will be 2 pairs in 1 month. One of these, namely the first, bears in the second month, and thus there are in the second month 3 pairs, so on and so forth. Now that was a little hard to understand, so let me break it down. It's important to realize, first off, we're talking about pairs of rabbits, not individuals. Each pair consists of 1 male and 1 female. And these rabbits, it takes them 1 month to mature to adulthood. So they go from babies to adulthood in 1 month. When they reach adulthood, they're able to have offspring. These rabbits are special. They never die, okay? They just keep living into perpetuity. Once they're adults, every month, like clockwork, they produce another pair of rabbits, their offspring. So Fibonacci was really asking, how many pairs will there be in 1 year? Here's a visualization of the problem. Here's our original rabbits. They came out of nowhere. But these are the baby rabbits. It takes them 1 month to mature to adulthood. So now at the end of the second month, at the end of the first month, they're adults. At the beginning of the second month, they're able to have their own offspring. This is the first generation of their offspring. They keep on living. Their first offspring take 1 month to mature. When they're mature, they have their offspring, this pair over here. They keep living. And these guys keep having their babies, and so forth and so on. So notice the number down the right-hand side where we're just counting the number of pairs of rabbits. It goes 1, 1, 2 pair, 3 pair, 5 pair, okay? So that is basically the Fibonacci sequence. It starts 1, 1, 2, 3, 5, 8, 13. Now, does everyone see a pattern? If you see a pattern, okay. The pattern is simply that the next Fibonacci number is the sum of the previous 2 Fibonacci numbers. So the next one would be 21, right? And it'd be nice if we had a mathematical notation for this. And of course there is. Here is the mathematical notation. Capital F means, I am a Fibonacci number. And the subscript indicates which one I am in the sequence. So F sub 1 is 1. That's this guy. F sub 2 is also 1. That's this guy. And from there on, we could just say f sub n plus 1 is equal to f sub n plus f sub n minus 1. In other words, the next Fibonacci number is simply the sum of its two predecessors. So my first challenge for you is to calculate f sub 10. This is not a test. You can consult with your neighbor, but I want everybody to make their best effort to just write down f sub 10. So right now we go 1, 2, 3, 4, 5, 6, 7. We're up to 7 here at 13. All right, I'm going to move on. Now I want to talk about numbers that have names. These numbers are so famous, they've been given names. And the first one we're probably all familiar with. It's the number pi, which is a letter of the Greek alphabet. So what is pi? Pi is the ratio of the circumference of a circle to its diameter. How so? Well, we all know the formula for the circumference of a circle. Circumference equals pi times diameter, right? So we just isolate pi. It's the ratio circumference to diameter of a circle, any circle. And its value is 3.14159, continuing indefinitely without a pattern. That's because pi is an irrational number. Pi also happens to be a transcendental number. The next famous number is E. It's known as Euler's number, named after the famous mathematician Leonhard Euler, who discovered it as the base for the natural logarithm. E's value is 2.71828, so forth and so on. E is also irrational and transcendental. Now I'm going to introduce you to a new number which has a lot to do with the Fibonacci sequence. It's also a Greek letter whose name is Phi. Phi's name was chosen to honor Phidias, who is the artistic director for the construction of the Parthenon, famous Greek sculptor who has also directed the construction of the Parthenon. We're going to compute Phi's value in just a little while. Phi also has a nickname. It's also known as the golden ratio. And we'll see why in just a bit. So let's see how Phi came about. First off, Phi has a one-dimensional interpretation. If you construct a line segment from this point to this point, so the total length is a plus b, and divided into two parts, length a and length b. Okay, so we just construct something like that, and we want to maintain these ratios. We want the total length of the line segment, a plus b, to a, the longer of the two line segments, to be equal to the ratio of the length of A to the length of B. Okay? Makes sense, doesn't it? And we're just going to give a name to that ratio. We're going to call that ratio phi. Besides and notice that phi is a positive number, right, just by construction. These are all positive numbers. A plus b, since b is not 0, has to be greater than a. So phi's value is certainly greater than 0, right? Everybody agree with that? Okay. Phi has a two-dimensional interpretation as a rectangle where one of the side lengths is a plus b. Again, we divide that side length into a and b. And the other side is just a. and we want to maintain these same ratios. Now, psychologists have done experiments where they've shown people many differently sized rectangles, and they asked them to take a survey at the end and say, which ones of these different sized rectangles do you find most pleasing? And people tend to choose rectangles that exhibit what's known as the golden ratio. In other words, this rectangle, they say it's beautiful. There's something about it. Okay, now there's time for some math. All right. We have these fundamental ratios, a plus b is to a, as a is to b, and we're just going to call that ratio phi. So our first step is simply to divide the expression on the left on both sides by a. So a plus b over a is simply equal to 1 plus b over a. But look, what is b over a? It's just the inverse of a over b, right? So because of that, we can write that it's equal to 1 plus 1 over phi, because phi itself is a over b. Now we have its inverse. But from the first equation, we have a plus b over a is equal to phi itself. So now we have the equation 1, phi is equal to 1 plus 1 over phi. And if we multiply both sides by phi and bring all our terms to the left, we have a quadratic equation. Does everybody see how we got there? Now, who knows a formula for solving a quadratic equation? I need somebody who's not a math teacher to raise their hands. Who knows the formula? Nobody. This requires some audience participation. Sarah.
X equals plus or minus square root of 4ac over 2a.
Yes. Sarah just announced the quadratic formula. So in general, it goes minus b plus or minus the square root of b squared minus 4a times c. That's all under this radical divided by 2a. So let's apply the quadratic formula to this equation where we have a is equal to 1, b is equal to minus 1, and c is equal to minus 1. So we'll just plug in these values here. So we have minus 1 plus or minus the square root of b squared minus 1 squared minus 4 times a times c. Well, a times c is minus 1. All over 2 times a, 2. Okay? So minus 1 is 1, plus or minus the root of, let's evaluate what's under the radical. Minus 1 squared is just positive 1. Minus 4 times minus 1 is positive 4. 1 plus 4 will give us 5 divided by 2. So we have just determined two values that solve that equation, but only the positive one is the value of phi, okay? Because this root is positive, this root turns out to be negative. And if you do just a little bit of extra algebra, you can see that the second root is 1 minus phi. So now I need someone to get out a calculator, or even your smartphone will do, to give us a numerical value for phi. Okay, so can somebody do that for me? You have to turn your smartphone sideways, probably. 1 plus root 5 divided by 2. You have it? All right. I'm not going to go for this. Thank you. All right, we have a numerical value for phi. Because of this square root of 5, we know that phi is an irrational number. However, because it's the root of a polynomial equation like this, phi is not transcendental. You have to be really, really special to be a transcendental number. Okay? Phi is irrational, but not transcendental. Time for some more math. We're going to start looking at the powers of phi. So this is our base equation, right? Phi squared is equal to phi plus 1, right? We saw how that came about. Pretty much our definition of phi. So let's multiply both sides by phi. We still have a balanced equation. Phi cubed is equal to phi squared plus phi, which I claim is equal to 2 times phi plus 1. Why is that? It's because we're able to do that substitution. Phi squared itself is equal to this, and then we can combine like terms and get the fact that phi cubed is equal to 2 times phi plus 1. Okay, let's consider the fourth power of phi. We just multiply through, and I claim that the fourth power is 3 times phi plus 2 because we've done 2 substitutions. We have a value for phi cubed, this value. We have a value for phi squared, which is this value. We can combine all the terms and come up with phi cubed, phi to the fourth is 3 times phi plus 2. We can keep going. I claim phi to the fifth power is 5 times phi plus 3. Phi to the sixth is 8 times phi plus 3. Now, just ponder the coefficients for a moment. Do you see a pattern on the coefficients on the right? You have 1, 1, 2, 3, 5. Yes, we seem to be duplicating the Fibonacci sequence. And it also appears as coefficients of phi itself. Here's 1, 2, 3, 5, 8. Only these Fibonacci numbers are just one step ahead of the ones for the constant. So we're going to form a conjecture. We're going to conjecture that phi to the nth power is f sub n, that's the nth Fibonacci number, times phi, plus f sub n minus 1, the preceding Fibonacci number. So that's worth writing down. Now at this point, we see a pattern, but we haven't proven anything yet. But we'd like to prove this so we can move on. So we're going to take a little bit of a detour, and I'm going to introduce you to the topic of mathematical induction. And this is an honored way of proving things in mathematics. And induction is like building an unbreakable chain. First, you have to prove something called the base case, which is like the first link in the chain. And then you have to prove the induction step. So proving the base case is like establishing the first link. And you can see this huge anchor link here. Does anybody think that they could physically grab it and just pull it apart and break it? Well, the links, the conceptual links in mathematical induction are stronger than the physical anchor link. Let me talk about the induction step. The way this works is that you assume the n minus first case is true and use that to prove that the nth case is true, okay? And if you can do that, you can extend your chain infinitely into, well, to infinity. So I am going to show you an induction proof on something not related to Fibonacci numbers. It's just adding, trying to prove what's the sum of the first n positive integers, okay? So I'll write it in this form. I'm asking what is 1 plus 2 plus 3, dot, 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 up to n, whatever we choose n to be. We could stop at 3. We could stop at 999. We could stop at really, really large number. So let's do the start at the beginning. Good place to start. What's the sum of the first one number? It's simply 1, right? What's the sum of the first two numbers? 1 plus 2 is 3. First three positive numbers, 1 plus 2 plus 3 is 6. The first four numbers, 1 plus 2 plus 3 plus 4 is equal to 10. All right, no question there. I just added them up. But now I'm going to give you an alternative form for the answer. I say that the sum of the first one number is 1 times 2, whatever that product is, divided by 2. And that's true, right? The sum of the first two numbers is 2 times 3 divided by 2. Sum of the first three numbers is 3 times 4 divided by 2. First four numbers, 4 times 5 divided by 2. So I hope you can see a pattern. What I'm doing is taking the last number, which is n in any case, it's our value n, multiplying it by the next number, its successor. So here it's 4 times 5. That product simply divided by 2. So that's going to be our hypothesis, that the sum of the first n numbers is given by the formula n times n plus 1, that quantity divided by 2. We're going to end up with an integer, right? Because either n itself is even or n plus 1 is even, right? Everybody agree? So here is a formula which the claim is gives us the sum of the first n numbers. It's known as a closed formula because somebody gave you the value of n. You could just plug it into this little formula, come up with your answer. You don't have to do all the computation to add up the numbers. And it'd be nice if there was a mathematical notation so you didn't have to write 1 plus 2, blah, 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 dot, 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 up to n. And there is. Mathematicians have agreed upon this notation. This is sigma, or actually capital sigma, the Greek letter sigma, capitalized. And it's saying, it basically means add. And what it's adding is this value to the right of the sigma sign. Just add the value of I. But we're giving where to start and where to stop. We're going to start I is equal to 1 and go up to n. And the claim is that's equal to n times n plus 1 divided by 2. And we'd like to prove that. Now, just as a historical side note, there is a story that the great mathematician Friedrich Gauss was in first grade, and as a punishment, his teacher gave his first grade class the job of adding up the first 100 positive numbers. And Gauss instantly thought of this formula, presented his answer to the teacher, and was right. So let's try to prove this claim, this conjecture, using mathematical induction. First, we have the base case, where the sum of the first one numbers is equal to this value. Of course, that's true. The base case is usually easy. Now we want to prove the induction step. So we assume that this is true. The sum from I starts at 1 to n minus 1 is equal to this formula, and we want to show that this is true. So we're going to assume this is true, and what we're going to do is add n to both sides of this equation. So now I'm writing this first one in long form, 1 plus 2 up to n minus 1. but we're adding n to that side, so there's the n, is equal to this thing, which we assume to be true, plus n. And then if you do some algebraic manipulation, you end up with the formula on the far right. So what do we have? We have the sum of the first n positive numbers is equal to n times n plus 1 divided by 2. We have assumed the induction step. It proved it turned out to be true, and we're done proving that. So we have a closed formula for computing the sum of the first n numbers. Let's get back to Fibonacci stuff. First, we want to prove this guy. That's our conjecture. So we have the base case, which is expressed phi squared is equal to f sub 2 times phi plus f sub 2 minus 1. And that turns out to be, well, that's pretty much our given. However, we span two Fibonacci numbers. So we have to prove the base case for phi squared and phi to the third. Phi to the third is phi squared plus phi, and we've already shown that's equal to 2 times phi plus 1, which follows this formula for phi to the third. We just substitute 3 for n. Now this is the tricky part, our induction step. We're allowed to assume that this is true, and we want to show that this is true. So we're assuming this is true, so what we're going to do is multiply both sides by phi. So now we have phi to the n equal to f sub n minus 1 times phi squared plus f sub n minus 2 times phi. But remember, phi squared is equal to phi plus 1, so we can do a substitution right there. And then when we multiply things out, we see we have a term here of phi, another term here of phi. We can combine these two. And we also have just a constant, f sub n minus 1, sitting there. So when we do some factorization and we realize that f sub n minus 1 plus f sub n minus 2 is equal to f sub n, we now come up with this form. We have phi to the n is equal to f sub n times phi plus f sub n minus 1. We've just proven that. And that's exactly what our goal was. So by induction, we have just proven that this is a true statement in mathematics. That's all a theorem is in mathematics. It's a true statement, something that you can prove to be true. In similar fashion, you can prove a statement about 1 minus phi. That's similar. It follows along the same lines, but I'm not going to show it here. It's also a theorem that the quantity 1 minus phi to the nth power is f sub n times the quantity 1 minus phi plus f sub n minus 1. So we have two true statements, two true equations. And equations, it's best to think of them as quantities on a balance scale. If the balance scales are even, then you can add the same quantity to both sides, right? They would still balance, right? You can subtract the same quantity from both sides, and they would still balance, right? So what I'm going to do is take this equation and subtract it from the top equation. And it'll still balance. We still have an equality. So all I did is subtract this bottom one from the top one. We get this form. And then we have to do some just some basic factoring to get it into this form at the bottom. And notice I have a quantity f sub n sitting by itself here. So it's multiplied by something. I'm just going to take that something and divide it into the left-hand side. And we finally have this form, f sub n, the nth Fibonacci number, is equal to phi raised to the nth power minus 1 minus the quantity 1 minus phi to the nth power over phi minus this thing, but the denominator simplifies to this form, and we have this thing that we've claimed is true. The nth Fibonacci number is precisely equal to that value. But we also have computed values for phi and 1 minus phi. We have precise values for those terms. So we can substitute them in the previous form and come up with what's known as Benet's formula, because a mathematician named Benet discovered this. The nth Fibonacci number is this crazy expression raised to the nth power minus this crazy expression raised to the nth power, all divided by square root of 5. Now I want to ask you, what did you get for f sub 10 from way back when I asked you to compute it? 55. But we just proved that f sub 10 is equal to this value. Didn't anybody write that down? No, anybody write that down? I'd be surprised. So I want to take a little poll. Now we know that f sub 10 is just a whole number, right? It's a positive whole number. But here we have an irrational value raised to the 10th power minus another irrational value raised to the 10th power. That whole thing divided by another irrational value. Who thinks this cannot possibly be true? Well, you guys have a lot of trust in mathematics. I was scratching my head when I first came across Benet's formula. But I don't want to arbitrarily claim that I know the answer. I'm going to ask Mathematica to compute it for us. And I have to explain what Mathematica is. Mathematica is a symbolic algebra package that knows how to do math. I have to admit, Mathematica knows more of mathematics than I do. And I don't know how it does it, to tell the truth. It's just a program. But here is a short program that I've written in Mathematica. And we're going to, and it's like a regular programming language. So this is one statement in the programming language. And first, I have to tell you something about programming languages that new computer science students always find confusing. They use the equal sign to mean assignment. The equal sign doesn't mean an equation. It means compute the value on the right-hand side, and whatever that is, store it into the variable on the left-hand side. So all that is in Mathematica is an assignment statement. And I'm saying, hey, Mathematica, give p, the variable p, the value of phi, okay? And Mathematica just echoes it back, says, yeah, I got it. And now I'm telling Mathematica the value of 1 minus phi. And I'm going to assign it to the variable q. It says, I got it. Now, if this statement is true, then I should be able to calculate the second Fibonacci number according to Benet's formula. And if you think back, that is the formula for the second Fibonacci number, because our power of n is just 2 there. So I'll say, well, what's f sub 2? And Mathematica says, that's 1. So we're feeling a little better, right? So my next step is to actually tell Mathematica, give it Benet's formula. And that's what this definition is going to be. It's Benet's formula, and I'm just telling Mathematica how to compute any Fibonacci number. And now I say, tell me f sub 10. And it gives me this mess back, which we didn't find too useful. But Mathematica has this wonderful simplify function. So I'll pass it the same value, Fibonacci sub 10, and ask it to simplify, and we come up with the value of 55. Is everybody feeling better? So the way Fibonacci formula works is somehow there are tons of cancellations in there, and it turns out to produce a whole number. I would not want to compute that myself. I don't know how long it would take me to simplify that. So is that all there is to the Fibonacci numbers? Of course, the answer is no. This sequence is tremendously rich in mathematical content, to the point where there is something known as the Fibonacci Quarterly. It's been published since 1963 by, of course, the Fibonacci Association. Here is the cover of one of the journal articles, and each article is some abstruse statement about the Fibonacci sequence, phi, the golden ratio, or golden rectangles. They have golden rectangles, they have golden triangles, they have golden polygons, and of course the golden circle, spire. So since I'm a teacher, I have to summarize everything that we've learned today. First, we learned that Fibonacci was a 12th century mathematician who documented his sequence in the rabbit problem. But more importantly, he introduced the Hindu Arabic numerals for computation to the Western world. Certainly a major contribution there. We learned about mathematical induction, which is a technique for proving theorems, and we used it to prove Benet's formula, that is a closed form for f sub n. That means we don't have to compute all the predecessors of a Fibonacci number to get its value. We can just go straight to the formula. We also learned that Mathematica says that f sub 10 is equal to 55. And we learned that there is a Fibonacci Quarterly, which documents ongoing research on the Fibonacci sequence. So now I ask, are there any questions? Yes?
Do these numbers apply to human populations? I was surprised to see that he calculated that on rabbits.
Yeah.
But my question is, do they apply?
No, I don't even think they apply to rabbits, because the rabbits live infinitely into the future. They always produce exactly one pair of offspring, one male, one female. That's all hypothetical. So now there's different ways of modeling animal populations and human populations that have nothing to do with the Fibonacci numbers.
Okay.
I think he saw the sequence first, and then he backed it into a word problem, where the rabbits were the word problem. Any other questions? Who noticed that the title, I really didn't go into the golden spiral at all? That's because I developed the presentation kind of after I gave you the title for it. It should be just called the Fibonacci, I think it was the golden ratio would be better than the golden spiral. Yeah.
I'm just curious what some of the things you're writing about in the quarterly. Like, what are some of the topics that,
Well,
you know,
like I
people are
said,
still
they
discovering
take,
about these numbers?
there's a strong geometric interpretation to the Fibonacci sequence. So once they discovered it in just rectangle shapes, they started looking for it in triangle constructions. There are certain kind of triangles where phi, the value of phi pops out if you consider certain ratios within those triangles. They also have found it inside of regular polygons and it's kind of like if you look hard enough for it, you'll find it. Yeah.
I just have a question. I don't know if there's any architects here or anything, but I know with that golden ratio and how you said people are
Yes, it's
pleased
pleasing.
by it, and it used to be used in architecture, like in Greece and that you could see the buildings done in that way. Is that still something that comes up in architectural classes here? I mean, here at all?
I think the answer is yes, but I can't say definitively.
That would be interesting research,
the-
wouldn't it, to see?
I've read contradictory articles concerning the Parthenon, where one author said, look, the world rectangle, it's all over. You look at it this way, it's here. Look at it this other side, it's there. Another would argue, no, it's not exactly the golden ratio. It's a little off, you know. It depends whether you include the steps leading up to the side and things like that. But it is true they've conducted psychology experiments where they show people different rectangles and which ones do you like the best, and they kind of focus on the ones that are approximately in the golden ratio.
I think when you look at rooms, like designs of houses, rooms
Yeah.
are shaped that way.
Right.
Approximately, so they
Yeah.
are very close.
Right, right. Of course, they probably don't come out to be an exactly irrational number, you know, like how can we do that? Does anybody want any little homework or learning math? You know? Here's a claim. Well, this is actually a theorem. Let me just leave you with this thought. You're given the number n. Say it's a real big number. And so it says, is this a Fibonacci number? And you say, well, how do I possibly figure that out? And do I add them all up, and once I get past it, I know I missed it? Or is there another way? Well, here's a claim. N is Fibonacci if and only if. Okay, so that's special in mathematics. It means it goes both ways. 5 times n squared plus or minus 4 is a perfect square. That means you can take that number, square it, multiply it by 5, and if that number plus 4 is a perfect square, or this number minus 4 is a perfect square, you can definitively claim that n itself is a Fibonacci number. So let's just see. This is one instance. This is not a proof. Our number 55. Either this is a square or this is a square, and it's true that 5 times 55 squared plus 4 is 15,129 is equal to 123 squared. And of course, this is offered without proof. I've seen the proof of this. Going from one direction is pretty easy, but going in the other direction is fairly hard. And that's a neat theorem in mathematics when you say if and only if. It means if somebody gives you this number, then you can claim that number is Fibonacci. Or if they give you this number and it's Fibonacci, then this is true. Any other questions? Yeah.
Headaches when trying to figure this out, or do you think they had many headaches just trying to come up with all the
Mathematicians, they always get headaches. That's what they do to themselves. I mean, I can't claim to do an original proof of any of these. That's what a mathematician does. He just sits there with pencil and paper, thinks really, really hard and deep, and this stuff comes into their brains. Right? And there's a great debate in mathematics whether it's invented or discovered. And this is worthy of a whole lecture itself, the philosophy of mathematics. Most mathematicians will say it's discovered, that this has always been there, their work, just they discover it because it's always been there. You know, you just have to look for it and know how to look. And other mathematicians, there's a school of thought say it's just invented from the minds of man, mathematicians, and you know that's where it comes from. But it's a fascinating topic in itself. Yeah, I didn't talk about the sunflowers. That's another lecture too.
I'm afraid we ran out of time. I want to thank Robert for this very elegant presentation and present him with certificate of appreciation on behalf of STEM. Robert was very generous. He declined the honorarium. So the amount, the dollar amount of $250 remains in the pot, which was contributed by Pearson Education. And once again, I thank you.
Okay.
Don't forget to sign in.